Today we are discussing a different subject. Today we are going to discuss analog and digital communication. So when we are talking about analog and digital communication, as we know, and we have already gone through AM and FM. AM and FM, that is amplitude modulation as well as the frequency modulations, are the two techniques which are used in radio communication system, and these are the wireless communication systems where a communication channel is provided and information has been broadcasted to multiple users that can be received and that can be used for multiple purposes. Now all these communication systems have some flaws. What are the flaws? These systems have the problems of noises. Every time a communication system has been designed, we need to understand that there will always be a noise. The noise was created due to that particular system, due to the receiver side. Like if you have a receiver and it is a wireless system, there are multiple problems, multiple things like there is an electricity hazard out there, there is a problem of lightning out there, there is a short noise, there is a thermal noise in that particular system that can create a problem. So multiple components which are used in that communication system can create noise, and when we cannot get rid of that noise properly, then we don't have a proper signal. If we don't have a signal, what we have is a problem that is continuously increasing at receiver side. So if we cannot communicate and we will not be able to establish a proper connection between transmitter and receiver, there is always a problem. So what we can do is we can design a particular channel. We can design a particular channel where the noise quantity will be lesser. Yes, noise quantity can be lesser, and it cannot happen one day. Now what we can do is we can design a multiplexing where multiple analog signals can be sent over one communication channel, like in AM, like in FM. We have been doing it quite frequently. Now what is the problem is that whenever we have this analog signal, and it is whenever we have this multiple factors like multiple channels are there and multiple equipments have been used, every time a particular equipment have been used will have some kind of noise, and that particular noise will create a problem. Now what we'll have is at the receive side, whenever we are getting a signal, that signal is distorted. Now that distorted signal is actually the lack of information. So what we can do is we can minimize that noise. Now how we can minimize that noise? Like there is a possibility then we can send a whole signal through amplitude modulation. We just put a carrier over there and use that particular carrier signal and change the amplitude of the signal. That what we have done is an amplitude modulation. Or what we can do is we can do angle modulation. Or in angle modulation, in other words, there is the FM, the frequency modulation is there. Like we just modulate that frequency and that carrier frequency will be there. That higher carrier frequency will actually help us to narrow the bandwidth, narrow the bandwidth and lesser the noise. That is the actual mantra, but that again is band limited. So what is the next phase? What is the next remedy of that thing? Now what we can do is we can have that particular signal converted into digital signal, or we can make particular signal into multiple parts will be chosen. Those multiple parts are called samples. Now those samples can be sent to the receiver side, and then they can be actually joined together to make the information which was actually initially broadcasted earlier. Now these can be taken. Now when these samples were taken at continuous intervals and they were multiplexed together, then this type of multiplexing is called time division multiplexing. And as we know that these signals are actually uses in pulses. So this is called pulse modulation. This kind of modulation is called pulse modulation, And this type of multiplexing is called time division multiplexing. What we do is we just take a particular intervals, and every time we choose those intervals according to our needs, and then we send those signals. Now, whenever we are taking a particular sample, this technique is normally called pulse amplitude modulation. So what we need to understand is why we are doing this, why we need to do all these activities. Now, if we have been talking about noise quite frequently. Now, what is that noise? Is that like if I am saying and I am just conveying a particular message like this now. Now, if I am not talking in the same language, so that can be considered as a noise. Yes. So any irrelevant information in any relevant signal can be considered as noise. Now that noise, now we have is we can send those signal over wired network or a wireless network. Yes, in wireless network there is a possibility that the thermal noise is there and short noise is there. So what? If we are using a wired network continuously for a longer period of time and longer distances, the cost of that network will always on the higher side, and there will always be a possibility that noise will eliminate the actual signal, and that distorted signal will not serve our purposes. Now, what is the problem in this is, like if you are talking about a particular wired network, for example, let me take one example for you. Like if you are talking about one telephone line, if you are talking about a 1 kilohertz signal, and telephone cable that is used for that particular signal will have attenuation of the order of 1 dB per mile. Now if you are talking about 300-mile run, this particular signal, and if we want to send a particular signal, and if that signal's strength at the receiver side is 1 millivolt, then the transmitting end, if we want to get the same signal which is sent over the transmitting end, right now we are talking about 1 millivolt signal, what we need to do is 10 to the power 147 volts. That is the power, that much voltage needs to be provided if we want lesser distortion or no distortion at all. So this is what I am talking about. If we want to send a signal, and that is literally impossible. Like if we have been using in telephone lines, what we are using is 48 volts. Like if you are talking about 10 to the power 147, if that idea is literally actually creating a problem for everyone. So that much power needs to be generated at the transmitter side for a wide network, and that is literally an impossible task for everyone. So what we can do? What we can do is we can have a different method. Now if we are talking about a different method, what we can do is we use amplifier circuit. Amplifier circuit has been used quite frequently. Now what we can do is, whenever we have a signal, like this is the transmitter side, and there is a communication channel, and this is the receiver side. Now this communication channel will have repeaters. Now these repeaters, whenever we are saying repeaters in communication system, whenever we are saying repeaters, these are actually the amplifiers. What they do is they increase or amplify the signal's strength. Now if you are talking about signal strength, so noise part will be there. Obviously we can't get rid of that noise. So till the time, if we are talking about this repeater, if we are putting the repeater over there in that particular point, so it actually amplifies the signal as well as the noise, but only the noise which is available to that extent, not above, not below, only that extent. Now every time we are using a repeater, we are actually amplifying the signal. What we will have is better SN ratio, the signal to noise ratio will be better, and what we will have is if we have a better signal to noise ratio, then there is a possibility then we can get the actual signal which needs to be transmitted and which needs to be received properly. So we can use repeater circuits, but there is an extent by which we can use these repeaters continuously, because there is always a possibility that if we use too many repeaters in particular communication channel, then there is a possibility that those repeaters can create a problem, and those repeaters can actually amplify the noise part too much that the signal will be distorted. So there is always a decision, and decision is, we can say that we need to decide whether this is the right choice or not. So we can use the repeaters, but to what extent it depends upon that particular communication channel. Thank you guys. Now we will talk about the sampling theorem. As you have already understood that that particular signal needs to be sent for a communication channel, and we don't want to use repeaters, so many repeaters at that point of time. So what we can do is we can take particular samples at a particular different time difference. Now at particular time intervals, when we take those samples, what we can have is a particular samples can be sent, and those samples, instead of sending a whole signal, we can send those samples, retrieve those samples and get the required output, required information. Now, sampling theorem is talk about this problem and how these samples can be collected, how these samples can be made and can be sent or a communication channel. Now let us suppose that there is empty, there is a baseband signal out there, that message signal is there, and we need to send it over a particular communication channel. Now this empty is a band limited signal, and their highest frequency component is considered as FM. Now if you are talking about FM, then sampling theorem suggests that TS, the sampling time or sampling rate will be always lesser than or equal to FM by 2. That is the maximum sampling time that can be achieved if we want to sample it, if we want to take a sample. Now it suggests that sampling rate should be rapid enough so that two samples taken corresponding to the highest frequency spectral component, as we have already understood that this needs to be done, that we needs to take particular samples at different time intervals. Now how we can take those samples? Just take this example. Now this is the message signal. Now when we are talking about the particular message signal, the message or this analog signal is like this. It is not particular amplitude followed, particular amplitude hasn't been followed. There is always a variations, like if I am talking in this voice, I can raise that voice or I can put down the voice. So there is a possibility. So if you want to send those variations, what I can have is, I have this message signal. Now what will I do is, this is the sampling signal. Now this sample signal or sampling signal will have a unit component of unit amplitude at a particular frequencies and at same time intervals. It is like the clock itself. Now this particular MT and ST needs to be multiplied. We have already done it FM and AM. We have done it through the carrier signal. Now this sampling signal will be multiplied in the multiplier, and the resultant signal is STMT. Now this, if you are talking about STMT, so what we can have is, when we are multiplying this thing, now what we result is, like this one is the amplitude signal, this one is the sampling signal. Now this sampling signal will be multiplied. So we will have this particular point, and these are the maximum limits of that particular amplitude because of that message signal. It will always have the maximum capacity of this one, but it will follow this path. So we will have particular points at which we can actually take the samples. Now these samples needs to be understood. How we are going to understand these samples. It is quite simple pattern. Now, whenever we are talking about these samples will have the same type of characteristics, and it will have the same type of phenomena by which it can be understood, it can be studied. Now, let's talk about the first signal. Now, if we have this is the empty, and ST has been sent, ST which is the sampling signal, where periodic train of pulses have been multiplied by this. Now what we have is that ST is the periodic signal with period TS and has the Fourier expansion. Now take the Fourier expansion. Now it is ST is dt by TS plus 2 dt by TS. Here TS is the sampling time. Again cos 2 pi T by Ts plus cos 2 into 2 pi T by Ts plus so on. Now if we take Ts Fm by 2, you can take it, that is the maximum limit of this sampling time. So we can take is Fm by 2. Here Fm is the message signals maximum frequency component divided by 2. Now if you are talking about this thing, then St MT will be dt by Ts MT plus dt by Ts 2mt cos 2 pi 2 Fmt plus 2mt cos 2 pi 4 Fmt and so on. Now this is how this resultant signal, this is the multiplied signal result of ST and MT. Now if you are putting this equation dt by Ts is there, and it will be multiply MT is there. Now in the next equation cos 2 pi T by Ts plus cos 2 into 2 pi T by Ts. Here is putting the value of Ts as Fm by 2. Whenever we are putting the value over there, we will get this output. Now, if you are Ts is 1 by 2 Fm. Let me correct myself. When we are putting the value 1 by 2 Fm, that is the value of that Ts. Now whenever we are putting the value over there, now the first term in C is aside from a constant factor. This is the constant. Again there is a multiplying factor and there is a sinusoidal frequency of 2 Fm. Now if you are talking about similarly DSP SC signal 4 Fm, 6 Fm is there. Now if MT is a signal, it is empty, we denote by MT, and it will have a spectral density, so it can be shown by mj omega, and that is now this can be shown in next figure. Now if you are talking about a particular signal, like if this is the component, now if you are talking about this spectral component, so F xt empty can be shown as if this is Fm, so this will be 2Fm, this will be 4Fm, and so on. So this can be shown like this. Now spectral signal can be shown like this. Now take this for example. Now we have already seen this, like this is the signal, and when we have this spectral component, like this is the signal, the message signal which needs to be transmitted. Now this signal, when we are multiplying this with the sampling signal, and when we have Fs, then when Ts is actually greater than 2Fm, there is a criteria that if it is greater than 2Fm, then there is a possibility that if we get this signal and we have this like this, if it is greater than 2Fm, then there is a band between two spectral components. Now this is the Fm, and if this is the highest spectral component of next spectral component is Fs, then this is Fs minus Fm. So this Fm to Fs minus Fm is the guard signal, is the guard band between those two spectral components. And if we actually put this Fs is less than 2Fm, then there is a possibility that these spectral components will overlap. It will run like this. It will run like this if you are talking about Fs is less than 2Fm. So there will be a frequency overlap in the signal itself. So what we need is, we need this guard band actually. But that cutoff frequency will not be like this, that the filter which we have been using, and that filter's cutoff frequency shouldn't be like this, that it shouldn't be sharp enough that it actually overlap or actually interfere in that message signal itself. So it shouldn't interfere in the message signal, and it should provide some band between two spectral components. This is what we need. So this guard band is actually provided when Fs is greater than 2Fm. Now whenever we are saying, if like suppose we are talking about voice signal, and if you are sending a voice signal over a telephone line, so that voice signal's Fm is 3.3 kHz and sampling frequency is 8 kHz. Fs is 8 kHz. So guard band will be 8 minus 2 into 3.3, that is 1.4 kHz. This guard band actually provides a proper signal at the receiver side. So this actually helps them to achieve that process. Now, whenever we are talking about this thing, a minimum frequency, that is 2Fm, at which this is the minimum sampling frequency at which this particular signal needs to be sampled, and this is called Nyquist rate. In several examinations, whether in GATE or engineering examination, semester examination, the Nyquist rate question has been always come. So Nyquist rate is 2Fm. So that is the maximum frequency component of that message signal. It is 2Fm, and this is the minimum sampling rate. Minimum sampling rate. Again, let me clarify. This is the minimum sampling rate at which that signal needs to be sampled. And if you are sampling it greater than 2Fm, there will be a guard band, so that by which we can actually provide proper guard, and we can actually distinguish between two frequency components. So this is actually needed, this is actually required. Now, for the sake of providing difference, we always put Fs greater than 2Fm. If we are putting Fs is less than 2Fm, there will be overlapping like this in two spectral components. So what we need to do is we need to have this sampling frequency rate greater than 2 FM, and this proves that if we are putting a particular frequency, that is 2 FM, greater than 2 FM, so there will be a proper sampling and there will be a signal without any distortion. So this proves the sampling theorem itself. Now we will talk about the pulse modulation system. Now whenever we are talking about the pulse modulation system, what is the first thing which comes into our mind? The pulses are actually the samples that are taken at particular intervals. Now we know about this sampling theorem. If we know about this sampling, and we have already know that particular time interval, that is twice 2 FM, we take the samples, and that particular signal has been multiplied by that sampling frequency, sampling signal. Now what we need to do is we need to identify that every particular pulse modulation system will have its drawbacks. Pulse modulation system have its things. Now